So this brings us to conservation of momentum. And many of you were using this concept in class on Monday to solve some of these problems. And but I want to make it clear and when you can use it and when you can't, because like conservation of energy, you really can only use it in certain circumstances, or you have to make sure you're using it correctly. And so first let's define it. What do we mean by conservation of momentum? So any quantity is conserved when it's the change in that quantity is zero over a certain time period. So that basically means that the change in momentum over change in time equals zero. So this is the definition of a conserved quantity. But we also know that, and we just defined that the change in momentum over change in time is equal to force. And this force is actually the net force on all the particles in the system. So it's not just one of the forces acting, it's actually the sum of all the forces. You can call it F total or F net. We'll call it F net here, but we've called it F total in the past, or we've used the summation, the sum of all the forces. And so since we can see that the change in momentum over change in Tx equals zero, and that equals force, then that implies, of course, that this force net, the total force, is equal to zero. So what does that mean? That basically means that when the total force on a particle or set of particles is equal to zero, then the momentum of that system is conserved. And so again, if we have this delta P equals zero, it doesn't really matter what delta T is. You can multiply by it on both sides and you still get zero. It's telling us that PF minus P sub I equals zero. And that implies that the initial momentum is equal to the final momentum. We can rewrite each of these momentums if the mass doesn't change as basically the initial velocity is equal to the final velocity. And this is, of course, consistent with Newton's first law of motion, which basically says that an object remains at rest if there's no external net force acting on it, or if an object is moving with a constant velocity. In that case, it'll have a constant momentum, then that it will not change its velocity unless an external force acts on it. So this is exactly the same thing that we've already talked about, just now using a different language and talking about the momentum as the thing that is conserved. So now we can do this example of momentum in the y direction. So if we have this block, if it's sitting on a surface, there's some force due to gravity acting on it, which gives it a weight. But there's an equal and opposite force acting on it in the upward direction, which is this normal force. And so then, of course, this object is not moving. And in this case, then we can see that easily that the total force, or the force net acting on this block, is equal to zero, and that implies, of course, that the change in momentum of this block is zero. This is a really boring example, but it's just an example to show you that it's not that there are zero forces acting on this block, it's just that the sum of those forces is equal to zero, and that's what gives you the change in momentum equal to zero. Now we can do an even more complicated problem. So in this problem, we're going to have a mass. It's going to be moving with a constant velocity. And of course, because of this, we can say that it has some momentum, which is equal to mv. And I'm going to call this the initial momentum because we're going to have something kind of happen to this block. So what's going to happen to this block is that at some point while it's moving, its mass is going to break into two. And these two different blocks are going to move off with different velocities. So the first block will move off with half of the velocity of the initial block. And of course, the question is, what is the velocity of the second block? And so we can calculate this because in this system, even though it was moving, the fact that it was moving with a constant force initially and there's no external forces acting on it means that the momentum is conserved. So that means that the momentum of the initial block with mass m is equal to the sum of the momentums of this two blocks after they break apart. And so in this case, what we have actually is that the mass is changing and the velocity of these blocks is changing. And so we can write this momentum of these two new blocks that are made from the initial block. We can see that we get mv of the first block, where m is just m over 2 of the original block, and the velocity is the original velocity over 2. And for block 2, we have also m over 2 for its mass, but we have some v2 and we don't know what it is. Okay, so again, with keeping these equations in mind, we know that the initial momentum has to equal the final momentum. So that tells us that mvi has to equal mvi over 4. So how did I get that? I just took this first term, which is the first block, and I know that the velocity of that block is vi over 2, so I just said mvi over 4 because there's two 2's on the bottom. And then the second block is mv2, which is v2 is what we're looking for, over 2. We can cancel out the m's from all of this, and we can multiply both sides by 4, so that gives us 4vi is equal to vi plus 2v2. We can gather all the vi's together, so that gives us 3vi is equal to 2v2. Divide both sides by 2, and we get that v2 is actually equal to 3/2 vi. So that means that that second block is actually going to move at a speed 3 times faster than the first block in order to conserve the momentum. We saw that on Monday in class, we did this little demo where two people sat on skateboards and then they could push off of each other. And this we again talked about in terms of, not in terms of conservation of momentum, but in terms of the center of mass and its momentum staying constant over time. And again, this is where these two concepts really do collide, and they're basically exactly the same thing. So what this means is that when you start with two objects at rest, and they have no internal force acting on them, or sorry, external forces acting on them, you can still have an internal force that can end up with motion, and the total momentum of the system will still remain constant. So what does that mean? You think of the two people pushing off of each other at like an explosion that had occurred that caused in this case, two people or two bits to break apart. And again, the total momentum of the system was 0 before and after because you include both people in it. But the momentum of each of the people was not 0. It's just that they were moving in opposite directions. So these momentums could cancel because momentum is a vector quantity. We also did the same example where we had a bigger person and a smaller person push off of each other. And what we saw again is that the total momentum was conserved, but that the smaller person moved much farther and much faster really is what it ended up being. And that the person with the higher mass ended up moving much slower. And again, the total momentum that was conserved.